Hello everyone, welcome to the second hands-on session. Um, Last time we worked on the functions and then we also completed them. And then we calculated the final form of the extended node list and we also calculated the stiffness, as you can see here. And today we're going to work on the post process for the previous example, which we had nodes at 0, 0, 1, 0, and 0.5 to 1. The triangular truss structure in the document. So let's start with defining a scale to exaggerate the results of the x-coordinates. So I'm just going to define this as 100 so that we can see it easily. We can see the deformation easily. So exaggeration. And then I'm going to define a list to store the coordinates of the final, or let's say the final coordinates of the nodes after they are deformed. So I'm going to compile this into a NumPy array later on, but we're going to start with the list. And we're also going to define an array to store the x displacements. I'm doing this because I want them to be in order, so I'm not going to use the extended node list. So after we've done that, we can start with the for loop. So for I in range np.size nl0. So I'm going to go through every single node, so this number will be equal to 3, which will give me 0, 1, and 2. Now I'm going to collect the displacements for each node. So we can take these with, we can take these from the extended node list. So if you look at the 8th column, this is the x displacement for each node. So that's why this is 8. And I'm also going to do the same thing for the y value. So this is going to be the 9th column, which will be this. And then I'm going to add these values to the original coordinates of the nodes so that we can get the final coordinates. So I'm going to add enl I 0, the first column, plus the displacement that we just found. And I'm going to multiply this displacement with the exaggeration value. So we will do the same thing for the y values here. But this time, this is going to be the second column. And then we're going to add the y values instead of x values. Once we've done that, we can add these to the lists that we just created. So we're going to append this with displacement x. And we're also going to append the coordinates with x and y values we just found here. And I'm also going to make these an NumPy array. So that's it. Finally, I'm going to compile them into NumPy arrays. So coordinates will be equal to np.vstack coordinates. I'm going to delete these brackets. And then we're going to do the same thing for the displacement. So disp x array is equal to disp x array. So I transform these lists into NumPy arrays, which completes the first part. Now, I'm also going to need to plot the colors and x and y values of the dots between the nodes. So in MATLAB, you can directly plug the x and y values of the nodes and the color values, and MATLAB will automatically interpolate between the nodes. But in Python, we have to use the scatter function to interpolate between the nodes. So essentially, I'm going to create dots between each node, and then we're gonna, we're gonna create so many dots that they will look like a line, a single line. So let's define another list to store these dots x values, and then create another list to store the y values of these dots. And finally, I'm gonna create a list to store the color values of the x displacements. So in your projects, you can also create color y and color stress, for example, to do the same for y displacements and stress plots. But since they're exactly the same, I'm not going to show it. So after you've done that, we can proceed with the for loop. So for I in range, this time I'm going to go through the elements instead of the nodes. So we have 3 elements. So this is going to give me 0, 1, and 2. And then I'm going to get, so in each element, we have 2 nodes. And each node has its own x and y coordinates. So I'm just going to get the x and y coordinates for these 2 nodes in each element. So let's say the first element's x coordinate will be this. So I'm getting the node number from the element list. I subtract 1 to get the index, because in Python the index starts from 0. And then I'm getting the coordinates from the final coordinates that we just defined here. So that's what I'm doing. It's going to be very similar to the second element's x value, but this time this is going to be the second element, so I'm going to change this with 1. And then we're going to do the exact same thing for y values, but this time we have to change these to 1 because it's going to be the second column in the coordinates array, because the second column represents the y values. All right. So once we've done that, we should also create another array to store the displacements of each element separately. So let's say numpy array. We're gonna have this x arrays. The first element's node number, I 0 minus 1 to get the index. And then for the second element, I'm just gonna copy this, paste it here, and then change this to 1. All right. Now we will have to use the slope of the lines to plot these dots. So if the slope is infinite, which will be the case where x1 is equal to x2, if we don't define a separate condition for that, the program will crash. So we have to define another if block here, if x1 is equal to x2, which is the case where the slope is infinite. And x is equal to np dot linspace x1, x2, 200. So essentially, I'm dividing the values between these two x values to 200 pieces. But in this case, it's going to be the same value throughout the whole NumPy array, but we have to do this to match the sizes of x and y values. So that's the logic behind it. And then we're also going to have the y values. So if we have two nodes vertically here, I'm dividing the line to 200 dots, and then I'm going to assign colors to each dot to make them look like a line. So that's what I'm doing here. Else, in other cases, we need to calculate the slope, which will be y2 minus y1 divided by x2 minus x1. You know this from calculus. That's it. And then we still need to divide x values to 200 pieces. This time, we're going to use the line equation from calculus to form these, let's say, dots into a line. So I'm using the slope that I found here. I'm using the x values here. And then to define this line, we have to take a point on this line. So x1 and y1 will be on this line. So that's why I'm using these. But you can also use the x2 and y2 values here. It doesn't really matter. So we created the x and y values for each dot. Now we have to append the list with these values. So it's going to be y, x, and then I'm also going to append the color values here. So color x dot append. Now I'm going to use the linspace here again, because as you know, the size of this NumPy array has to be the same size as these NumPy arrays, so that we can actually plot these. So I'm dividing the color values to 200 pieces as well. Inside this, we're going to have two values. We also want the color values to be absolute values here, because I don't want to see any negative values in the color bar or in the plot. So you just take the absolute value of the color values here. And then finally, we're going to insert disp xl0, so the first element's displacement from this array, and then the second element's displacement here. So that's it. So once we've done that, we can just compile these lists into NumPy arrays. So np.vstack. We're going to have xscatter. We're going to have the exact same thing for yscatter. And then we also need to compile the color values. So color x will be equal to np.vstack color x. What's the issue here? I think I made a mistake with the brackets. So linspace will take the whole thing. So I need this, and I'm going to delete one bracket from here. So linspace and then append. Linspace takes this. Absolute takes this. Okay, now it's fine. So we appended all these values to NumPy arrays. We also have to convert these NumPy arrays into 1D arrays to use them in plot. Use them in the plot function in matplotlib. So flatten this as this. That's it. Now, here we come to the plotting part. So let's first import this. So I'm going to import these again, just for the demonstration. You have to import matplotlib pyplot as plt. And then we're going to create the figure as, let's say, this figure is equal to plt figure 1. I'm also going to get the axis from this figure. So let's say this x-axis is equal to this figure dot at subplot 111. So I created the figure and then I got the axis in these two lines. Now, let's say that I'm going to plot this in jet color map. So you can choose any color map. I would like to use jet. You can use copper or, I don't know, bone, and etc. We have a lot of color maps in Matplotlib. You can just look them up. Now, we have to use these values to scatter the plot. So ax dispx, which is the axis we define here, dot scatter. And then we're going to use the x values here, y values here, and then the color will be equal to color x that we define here. So x values, y values, and the color values here. And then finally, we will have the color map as CMap that we define here. Now, since the scatter function will plot, single dots in a form of the line, I would like to make them look like a line from distance. So I'm going to set the size of each dot to 10, and then I'm also going to disable edge color to none. I'm going to set the edge color to none so that we won't have black lines around the scatter plot. So that's it. Now, we also have to import. So wait, before that, if you do this, I think I made a mistake somewhere here. Let's see. I forgot to add the final parameter here, which is 200. So don't forget about this, because the size of the color array has to be the same as x and y and x arrays. So don't forget about this. So now, as you can see, we can see the color distribution throughout the truss structure. If you zoom in, you can see that these are actually dots created by the scatter plot. But since we have 200 pieces between every node, it just looks like a line. So that's what these 200s do in this plot. Now, we would also like a color bar next to this plot. So I'm going to import two modules from Matplotlib. One will be from matplotlib.colors import normalize. And then another one will be from matplotlib.cm import scalar mappable. So these two are necessary for color bars. Don't forget about these. Now, I'm going to define a normalized function, a normalized color scale to use in the color bar for x displacements, which will be norm x. And I'm going to use a normalize function. So this will take two values, which will be the minimum value and the maximum value. So the minimum value will be the absolute value of the minimum amount of displacement dot min from the minimum value to the maximum value of the displacement x. So that's it. We also need to put this on the figure. So this figure dot color bar. I'm going to use the scalar mappable function. And then this is going to take the norm and CMAP as the parameters. So norm will be equal to norm x, and then color map will be equal to CMAP that we defined here. So that's it. If we do this, now you can see that at the very right side of the truss structure, we have 5 times 10 to the power of minus 4 displacement. And then at the very left side, we have 0 because this node was fixed. This node was free to move in the x-axis, and this node was free to move in all directions. So that's how you plot the results from a process. And this is how you do the post-process. Now that we're done with the calculation part, here's what your project should look like approximately. You can have your own designs in your projects, in your additional features maybe, which might grant you additional points. But this is the basic look of your projects. So the example that we worked on before is this one. So let's define the boundary conditions here, which will be for node number 1, the y displacement will be 0, and it's also going to be fixed in the x direction. And for the second nodes, it's going to be fixed in the y direction. So as I add these and press apply, it updates the plot. And then I'm also going to add a force here, which will be minus 20, as you can see here. And then here we have the material parameters. So if you run this, we can see the exact same results in our calculations before, but in a much nicer form, as I've integrated this into my GUI. So you can go between the x and y values here. So in the y-axis, if we apply a force on the third node downwards, it's going to have the maximum displacements on the y-axis. And then these two nodes are fixed in the y direction, so they're not going to have any displacement here. So you can go between these two values here. You can also see the stress on the elements. So elements will have this constant stress throughout the whole thing. So they're going to have a single color. So we don't have stress in here, but we have stress in these two elements. You can also go through the color maps. So this is copper, this is cool, this is magma, which is one of my favorites. I like this. And you can change these. And this is the value in the previous code, which was scale, to exaggerate the plot. So as I move this, it exaggerates the plot. Since the force is not really that much, it's not really that much, but you can still exaggerate. Now let's work on another example here. You can also import structures here. So let's say, which one was it? Yeah, this one. So let's say we have this truss structure here. Now, you can also, turn on and off the node labels and element labels, which is a cool feature. So that's one thing. It also shows the number of nodes and elements, as you can see from the plot. And yeah, so let's add the boundary conditions again. The first node, I'm going to fix the first node in the y direction, and I'm also going to fix it in the x direction. And I'm going to fix the 14th node in the x direction as well. And finally, I'm going to add a force downwards on the 8th node. Let's say minus 50 newtons. So if we apply that, it's now complete. And now if we run this, and since the exaggeration is too much, it's going to look like this. But if you bring it back, now it looks correct. You can see the values here, and you can still go between the x and y displacements as well. You can still change the color maps, and you can still exaggerate and bring it back, or you can go all the way to 0 to make it look like almost undeformed. So yeah, that's it. So you can also remove the whole thing. And one thing I want to mention is, let's say we're trying to generate the structure on our own. So let's say I have these 2 nodes, and then let's add the third one as the previous structure. So this is something different. Now, if I wanted to add a node in the same coordinate of the previous nodes, so let's say we have a node in 0, 0, and then I press this, I will get an error message, and it will not add the node on top of this, because we already have a node here. And it will be illogical to add another node here. So this is something that you should be careful about. That's it. And you also can't add the same element over again. So let's say 2 to 3 and 3 to 1. As you can see, the order of the elements doesn't matter. So if I try to add this again, it will give me an error saying element could not be added, element already exists. So that's one thing that you should be careful about. So you can use these structures as a benchmark in your projects to check the values if they're correct or not. So let's say this will be the final example, by the way. Let's fix this in the y direction and x direction as well. And then let's also fix this in the, let's say, y direction. And then I'm going to apply a force on the third node here in the x direction, let's say, 50 newtons. Now, if we minimize this, now I can see that the structure is like this. And let's run this. Now I can see that the values are as follows. You can still exaggerate. It will move to the right side as expected as we exaggerate. And this is pretty much what you're looking for. This is the y values, and these are the x values. So yeah, that's pretty much it. You can also see the previous structure in the behind, so be careful about that. That's a great addition. And yeah, that's pretty much all of it. I hope you guys got everything that I've said. You can email me about this whole project. If you have any questions or if you're stuck, I'm going to leave my email in the description below, so you can contact me through there. And that's pretty much it. I'll see you guys in the next hands-on session. Take care.